Good afternoon, everyone. So my name is Angela, and I come from Portugal. And the work that I'm today, I will tell you how we can use astroseismology to study and to search for activity cycles in other stars or activity in other stars. And in particular, in this work, we look for signatures of magnetic activity in the seismic data of solar-type stars observed by Kepler. So solar-type stars, as the name indicates, are stars that are similar to the Sun. So they are cool, low-mass stars, and they have convective envelopes. On one hand, the convection is one of the key ingredients for magnetic cycles for magnetic cycle in the Sun, and on the other hand, these convective motions also excite acoustic oscillations that travel through the interior of the Sun. And one way that we have to study those acoustic oscillations is through the brightness variation of the Sun or other stars. So here we have a light curve for the Sun, flux over time. And to better identify the different components for the contributions for the brightness variations, we usually study the power spectra of the light curves. So this is power spectra of the solar light curve, and I will come back to this later. We have different components for that contribute to the brightness variation, but for now I want to focus on this bump here, and this corresponds to the P modes, the acoustic modes of the Sun. And if we zoom in this frequency range, so this is how the P modes look like for the Sun. And by studying the properties of these acoustic modes, we can learn about the internal structure and dynamics of the Sun. We can learn, for example, about stellar internal rotation, about chemical composition, evolutionary state, and so on. And we also can learn about magnetic activity. And in the Sun, as the activity level changes over time, here this is for solar cycle 23, and magnetic activity changes, affects the medium where the waves are propagating, the properties of the waves change over time as well. So in this plot, we have the variation in the amplitudes of the acoustic modes over time. So here is the solar maximum around 2001, and we have the amplitudes of the acoustic modes decreasing with activity level. So the magnetic activity suppresses the acoustic modes. For the frequencies of the acoustic modes, we observe the opposite behavior. So these are the frequency shifts. This is the variation in frequency in relation to a reference value, that is the mean frequency shift. And so these are frequency shifts over time, and we have the frequency shifts increasing towards 2001, towards solar maximum. So the two properties, the amplitudes and frequencies for the Sun, are observed to vary in antiphase with time. The frequencies increase with activity level, while the amplitudes decrease. And the frequency shifts, so this is mean to maximum shift. So the frequency shift between maximum and minimum as a function of frequency of the modes. So, and we can see here that the frequency shifts is strongly dependent on the frequency of the modes. And the modes with higher frequency have larger frequency shifts. So these modes of larger amplitudes higher frequencies, sorry, are the modes that are most affected by the activity. At the same time, these modes are the ones that are these modes are more sensitive to the outermost layers in comparison with low frequency modes. So this dependency of the frequency shifts in frequency led to the conclusion that the origin for the frequency shifts that we observed through the solar cycle is located in the outermost layers of the Sun. But still, we don't completely understand the different contributions to those frequency shifts because there are different phenomena that are changing in the sun. We have the solar magnetic cycle, the global solar magnetic field that is changing. We have the number of magnetic features changing. There are different magnetic features, and they can contribute with different effects, thermal, structure, or direct effects. So, but still we have evidence for the main contribution for frequency shifts to be the weak component of the magnetic field. But the strong component still has a significant effect for the frequency shifts. And this strong component is related with active regions and in particular with sunspots. So besides this long-term variation in the frequencies of the acoustic modes, the frequency shifts are also vary in shorter time scales, and they are observed to vary on a quasi-biennial time scale. So these are the frequency residuals. This is for solar cycle 22 and 23. And the frequency residuals are the frequency shifts after removing the long-term variation. And the different colors correspond to different frequency ranges. And the first conclusion was that these residuals have a periodicity of about 2 years. And the second conclusion was that these midterm variations don't depend significantly on the frequency. This is the opposite to the long-term variation. So this week, so just to show you here, this is before removing long-term variation for the same frequency ranges. This is high frequency range, low frequency range, and the amplitudes of the frequency shifts in the long-term time scale are very different. So this weak dependency of the quasi-biennial variations suggests that these midterm variations are the origin for these midterm variations is deeper in sun than the origin for the long-term frequency shifts. Different frequency ranges for the modes. So the same as here, but basically they took different frequency ranges, low, mid, and high frequency ranges. And they have here they are displaced just to illustrate, but these are the frequency residuals for different frequency ranges. And the amplitude does not vary much. So this is basically the summary, a brief summary for what we know for the sun, how the properties of the acoustic oscillations are affected by magnetic activity, but we expect that these kind of activity-related variations in the seismic properties of stars or seismic properties are common among solar-type stars. This is because we expect that solar-type stars have acoustic oscillations, and we expect that those stars also have magnetic cycles. And this corresponds to the first detection of those such variations in a star other than the sun. So this is a star observed by Corot. This detection was made by Garcia et al. In 2010. And in this first panel, they have the amplitudes of the acoustic modes. Here, the frequency shifts. And here is a star spot proxy computed from the light curve. So they found the amplitudes and the frequency shifts varying in antiphase, just as the case for the sun. And they also found the variation in the star spot proxy consistent with the magnetic cycle. So this was the first detection. And last year, Salaberto et al., same group, they detected for the second time the frequency shifts, activity-related frequency shifts for a star, this time observed by Kepler. So the different symbols correspond to the frequency shifts obtained with different methods, but we can focus on this one. So the squares are frequency shifts in the solid light corresponds to the SPH index. So this is a star spot proxy a photometric activity indicator also derived from the light curve. And they found the frequency shifts and the SPH varying more or less in phase over time. This was the second detection, and since then there are two more studies where they have looked for, searched for frequency shifts, and for now, and there are evidence for activity related in at least 9 solar type stars. So this suggests that we can use asteroseismology to learn about the activity-related changes that take place in the interior of stars. And Kepler provides a unique opportunity to study and characterize those magnetic cycles. And in this study, we also want to try to answer this question: is the granulation affected by magnetic activity or not? So granulation is related with convection. And just to show, I will not enter in details, but these are the summary for the Sun. So the check marks mark the evidence for the properties of the granulation being affected by activity, while the crosses mark the cases where there's no evidence for that. And so this is still matter of the argument for discussion in the literature, and for other stars, it is also not well established as well. So in this study, we analyze a large sample of stars observed by Kepler, solar type stars. In order to analyze those stars, we have developed the Bayesian peak-back tool, and this tool allows us to obtain the properties of the acoustic modes. And then we search for temporal variations in those properties and compare with other activity indicators and hopefully characterize stellar magnetism. So our sample is composed by 87 solar type stars. This sample is composed by other two samples. The legacy sample is a sample composed by 66 solar type stars, high signal to noise solar type stars, and this is a subsample that have 4 common stars with the previous, that is composed by KOIs, Kepler objects of interest. So stars that are confirmed to be planet hosts, or to be confirmed, or still to be confirmed. This is just the HR diagram showing our sample. Then we use short cadence data obtained with a cadence of 1 minute, and this is because we want to be able to detect solar oscillations. And then for each time series is split in shorter sub-series in order to look for temporal variations in the frequencies and in amplitudes of the acoustic modes. For some of the stars, we have 4 years of data. And for each subseries, we then study the power spectrum of each star for each subseries, and we model it. So this is basically our model. This part here corresponds to the acoustic modes that are modeled as Lorentzians, and this is where our peak-back tool enters. And this component here corresponds to the background signal, and this is determined in a previous step to the peak-back analysis. So coming back to this picture, so this is power spectrum of the Sun, and the background signal here is basically composed by the activity component, the granulation component, and faculty component. These two components are related with convection, and in particular for Kepler stars, we still have to add a flat component related with photon shot noise. So in the end, we start with a model composed by 4 components: activity, granulation, faculty, and photon shot noise. This is the power spectrum of one of the stars in our sample, with different smooths in black and gray. And in this process, we also remove, we neglect while determining the background signal, the low frequency range, which is dominated by the activity component. And we also remove the P envelope from this fitting. And just to say that nu max is more, corresponds to the frequency of maximum power in the oscillations, so more or less the center of P modes. And for most of the stars, we actually found that this second component, Faculae component, is not significant enough, and therefore our final model is only composed by these three components. So just to mention here, this is the amplitude of the activity component is modeled as a power law. And this is the granulation component, modeled as a RV profile. This is amplitude, the granulation time scale, and the slope of the power law. And this is a constant component. This corresponds to the best fit to this, the power spectrum of this subseries. And just to show another example, here for this star, we also have the model more or less in agreement with the power spectrum. And we did that for every subseries and for every star in our sample. And to check if our models are reasonable or not, we also look at the relation between the granulation time scale and nu max. Nu max, as I said, is the characteristic frequency of the acoustic modes, and this is the characteristic time scale of the granulation component. And these two should be related because convection is the process behind the two, the acoustic oscillations and granulation. And this is the theoretical prediction. So theoretically, it is predicted that the granulation time scale of the granulation component scales with the inverse of nu max, and it was also confirmed with observational data. And this is our results. So these further confirm that our models are reasonable, our models for background. So the models for background are now fixed for each subseries of each star, and we model now. We start the peak bagging analysis. So these are the wave numbers, radial order, the angular degree, and azimuthal order. This is a relative amplitude of the modes of the different azimuthal orders, and it depends on the inclination of star. This is one of our free parameters. This is also relative visibility now for the mode of degree of a given degree in relation to the L equals 0, and this is the height of the mode. This is also a free parameter. This is the line width, also free parameter, the frequency of the mode, and here we have the rotation, the splitting due to the rotation. So we end up with these free parameters in our model, and since we are following a Bayesian approach, we have to assign prior probabilities for our parameters. I will not enter in details, but just to mention that we use prior results to constrain our priors, because these stars were analyzed, the full length of the time series were analyzed in previous studies. Now we are analyzing shorter subseries, but we use those results, the frequencies and of the modes, and the results for rotational splitting and inclination of the star. We use those results to constrain our priors. And then for the fitting methods, we use this algorithm called MC. Is a MC code, but designed to reach a better mixing of the a better sampling of the perimeter space. And from this analysis, we get the posterior distributions for the parameters in our model, and from them we get parameter estimates. So these are the same two stars as before. now we have the power spectrum zoom in the region of the acoustic modes, and in black and gray are again the observed power spectrum, and in red we have the best model that fits the power spectrum for these two subseries. So at this stage we already have mode parameters, amplitudes, line widths, and frequencies, and we now can compute the temporal variations, and we compute the frequency shifts in relation to a reference value, that is a mean frequency of the modes, and then the final mean frequency shifts are computed as a weighted mean of the frequency shifts for each mode. And we do the same for the heights of the acoustic modes, but now we use logarithmic heights, because this parameter follows a log normal distribution and not a normal distribution. And first, before applying this method to Kepler data, we also applied it to solar data, a real and artificial solar data. And here, just to illustrate one of the tests. So this is for Virgo data. In black, we have the results from our analysis, frequency shifts, and the heights of the acoustic modes. And in green, we have the 10.7 centimeter flex. That is a proxy for the solar activity. And first, we obtain the correct amplitude for the frequency shifts. These frequency shifts also agree well with the 10.7 centimeter flex. And we also found the amplitudes to be more or less anti-correlated in time with frequency shifts. So this was one of the tests, and then we applied to Kepler data. I will show the results for 4 stars. So this is the first star, Doris, and here in these two first panels we have the seismic indicators, frequency shifts, and logarithmic heights of the modes. Here we have the SPH index, the same index that I mentioned before, the photometric activity index. And here we have the granulation, timescale granulation, or timescale of the granulation. So in black here, this corresponds to our results from the Big Bang analysis, and in blue we have the results from a cross-correlation analysis. And the goal of this comparison was first to check if our results are consistent with other methods, and second, to check if we are able or not to get smaller error bars. And we also were able to get smaller error bars. And we found the frequency shifts increasing with time for the star, while the amplitudes are decreasing, so just similar to the Sun. And the SPH also seems to vary in phase with the frequency shifts. So this comparison is suggesting that these frequency shifts are activity related. For the granulation timescale, we have some variation, but it doesn't seem to be related with variation in the other indicators. This is a second star, so we have the same properties: frequency shifts, heights, SPH, and granulation timescale. And for this star, we found the frequency shifts varying in phase with the heights of the modes, and this is not this was not expected based on what we know for the Sun. And these frequency shifts are also in phase with the variation in the granulation timescale, and in the SPHG index there is also some variation, and these high levels of SPH coincide of large values of frequency shifts. So for this star, all the parameters seems to vary in phase, and this was not expected based on what we know. And this is Mowgli. So this is the star of the second detection of activity-related frequency shifts that I showed before. Here we have the frequency shifts, and we can see some variation here that seems to have 2 cycles at least. For the logarithm height, we didn't found a strong variation, but there are still some evidence for an anti-correlation with frequency shifts. And here this is the SPH that seems to vary more or less in phase with the frequency shifts, and also the granulation timescale also seems to show a variation consistent with the previous properties. So this is the last star that I'm going to show. For this star, we also found the frequency shifts increasing with time, while the amplitudes decrease, similar to the first star that I've showed and to the Sun. And the SPH is also very in phase with frequency shifts. And for the granulation timescale, there is no significant variation. And then we look at the results for the ensemble. So we have performed the same analysis to every star in our sample. And here we have the frequency shift amplitude. So corresponds to the difference between maximum and minimum as a function of the effective temperature of the stars in our sample, color-coded by the age. So here, these results seem to suggest that the frequency shifts increase with effective temperature, and this is in agreement with previous theoretical predictions by Metcalfe et al. 2007. And here we have the frequency shift amplitudes as a function of the rotation period of the star. And we found that at least our results suggest that frequency shifts increase with decreasing the rotation periods. So faster rotators have larger frequency shifts, and this was also more or less expected because we expect that solar type stars that are faster rotators are more magnetic, more active than stars with longer rotation periods. So I leave you with the summary of our results, but I want to conclude saying that this is just the beginning of what we can do with asteroseismology in studying magnetism in stars. And we actually can use asteroseismology to search and detect magnetic cycles, but more important, we can use asteroseismology to learn about stellar magnetism, and hopefully also to learn about the magnetism of our Sun. And we also can use asteroseismology to learn how magnetic fields evolve in stars, and how the evolution of stars is also affected by magnetic fields. So thank you very much.
Angela, you showed right there at the end how the frequency min to max varied with rotation rate or with surface temperature. Have you also looked at the same thing, not for the actual frequency shift in microhertz, but rather the fractional frequency shift? So the frequency range divided by the frequency maximum?
No, we have not looked at that. Sorry?
If you backed any of the measurements up with direct spectral polarimetry of these stars, or any of them, or a subset thereof?
No.
Right? So you can infer the magnetic field cycling directly without having a. Then you find a bright enough example that you could test it on.
So we need a bigger.
Oh, of course.
So
Use geekits.
we did get a null dissection with a 4-meter telescope on the brightest magnetically active star. No signatures, but most of the stars are
bunch of different components to the total spectrum. There was the component, for example, from flares and faculty, I think. How do these other components vary with the cycle? Can you make equally interesting statements about it?
Wait, sorry. So this changes with cycle. This is this component on low frequency range is related with active regions.
Yes.
This component is one that we are trying to say something about that because they are still evidence for both being affected and not being affected. The amplitudes of the granules and the time scale of granulation. There are studies that say that they vary with activity, and others that they don't vary for the sun and for other stars. So hopefully, in the end, we can say something about this granulation, this component being affected or not by activity. This component is still related with the granulation, so for my stars, I'm not using this component. I'm not fitting this component. But I would say that if the granulation component is affected, this should be also affected. So with P modes, and P modes are the ones that we are looking for the frequency ranges, frequency shifts, and the variations in the amplitudes.
So you have the fit components for all these different pieces of the spectrum as time series.
Yes.
Are they published on the paper?
We are writing the paper, but yeah. Here I just show the one of the parameters of the background signal. This is the granulation time scale, but we actually have all the other parameters. Yeah.
So on your rotation and frequency shift amplitude plot, your foolhardy might try to fit power law or something next to that. So trend, but I think if you take everything after 15 days, you'd say you just look at that, you'd say there's no correlation between these
Yes.
rotation. Comments on what that might mean? What's causing the frequency shift amplitudes?
I would say that 4 years.
Yeah.
The cycles are much longer. You only have 4 years.
Yeah. For most of the stars, we have like a lower limit of the frequency shift amplitudes. For example, this star is already decreasing, but we don't know. But here we don't know if the cycle is still going on, and this is the maximum of the cycle, or so this is basically a lower limit for some of the stars. So yeah.
You take the sun just in the maximum, for example, and you do 4 years, you never find that it's
But I don't think it helps. I mean, so it makes it a lower limit. That means at best you could move the points beyond 15 days up, right? Move some with the larger amplitudes. They wouldn't find a trend that continues with, let's say, the one to the left.
What's the high point? 30 days and because
Doris.
of the sun. Huh?
Doris.
That's Doris.
Yeah.
Medalist. All helpful. Yeah. So, if you go back to this various distributions plot, now solar supergranulation does vary in scale over a cycle. So, is that what component of the granulation is supergranulation versus granulation? Because the supergranulation does vary in scale, which means that your sources of your PMOS also varies in scale. How does that feed back into this mix? I mean, I guess you can maybe only see the effect of it, but not, do you know what I mean? You can see the byproduct of that scale changing, because it's going to feed back in your calculation. Because your PMOS will have different L's at different times of the cycle, right? So your actual L numbers are shifting around.
I have no idea how to change the scale of granulation with time spectrum.
basically in this plot is going to be the granulation, and the granulation is going to be something like meso or super granulation. We have this discussion forever. So it's no, it's just a matter of it's scales of convection.
Yeah.
We don't have any idea of which one it should be. It should be the closest to this to the mode should be the granulation because this is the one that is exactly the mode, right? But it's precisely the one that we have a lot of trouble to measure. So we used to say granulation is the one that we always see.
Yeah.
But
the way that you identify the different components is based on the frequency of domain in which they live, right? Right. The time scale is where the bend is, right?
Yes.
So what's the relative time scale of what you call super granulation? A few days. So 2 days versus 10 minutes.
Yeah. I'm not sure if someone looked at that. Do you know? No.
There's almost no degree difference.
Yeah.
You plot against frequency. You plot it against frequency. Is that different L?
Yeah, that one.
Yes.
That's
These are different
L range.
data.
That's different L ranges, right?
Yeah, and they're all on top.
This is yes, and this is for the different data. This is Gong data, and this is Bison data.
So your estimate was quasar to the
Yeah, different L's are different lower turning points, but I don't think someone looked at that. I don't know if maybe they looked at and they didn't found any variation with L because I don't recall to